Alright, hey everyone, we're live. So today was the CodeChef 2021 August Cookoff, and as has become the usual, I'm going to go ahead and talk through all of the problems that I solved. And that includes all of the problems from Div 3 and Div 2, and then everything from Div 1 except for construct a string and maximum tree jumps. So we're just going to go right in order. I'm going to start with the Div 3 and Div 2 only problems. So which division, then equal difference, then team formation, and then chef enclosure. And then I'll go through the problems that are from the Div 1 contest. So different string, clear the array, odd array, interactive equivalency, and then chef to chef. Alright, so starting with which division. We're given an individual's rating and the bounds for the three divisions, and we have to output which division this person is in. So this obviously is just a pretty straightforward implementation problem. So as long as you have a general idea of how to implement conditionals in your programming language, this should be pretty immediate. What I do here is I just say if the rating is less than 1600, then we're dealing with division 3. Otherwise, if it's at least 1600, then we've got either division 1 or 2. And if it's less than 2000, then we know it's division 2, and otherwise it's division 1. Yeah, pretty straightforward. Not a whole lot to talk about here. Okay. So now let's talk about equal difference. So we're given an array of n integers, and we have to find the minimum number of integers that we need to delete from the array, such that the absolute difference between each pair of integers in the remaining array will become equal. Oh yeah, someone's asking if I can make the text larger. Yes, I will do that right now. There we go. Okay, cool. Yeah, this should be better. So first of all, notice that this is equivalent to finding the minimum number of integers you need to delete is essentially equivalent to finding the maximum number of integers we can keep, which is maybe in this case an easier form to think about, because it turns out that there are a lot of things we can say about a set of integers that we can keep such that the absolute difference between all of them is equal. And so here, from here, there's a couple of mathematical observations. So first of all, let's talk about the array after the process is completed. So the first observation that you should make is, suppose that A contains two equal elements. Then every element of A must be the same. And the idea here is, let's say that that two elements of A are equal to X, then the common absolute difference has to be the absolute value of X minus X, or 0. So every two elements have absolute difference 0. So every pair of elements is equal, meaning all elements are the same. And so what this tells us is that A is either a bunch of numbers that are all the same, or it's a bunch of numbers that are all different. And to handle the case where every number in A is the same, we can just iterate through all the possible values and pick the one that appears the most times and keep that one. So for example, in this second sample case, we would keep the choose because they appear 3 times, and we could get 3 choose, and then we would drop out the 5 and the 1. Okay, so the other case is when so say that every element of A is unique. Then what I'm going to claim is that A contains at most 2 elements. And the idea here is this. Suppose A contains the 3 values X, Y, and Z, where X is less than Y is less than Z. Then we can see that the absolute difference between X and Y is Y minus X, and the absolute difference between Z and X is Z minus X. But these two things are not equal, clearly, because Y is less than Z. And so basically, if we have 3 distinct values, then the smaller gap between x and y, or the smaller gap between y and z, cannot equal the larger gap between x and z. And so these absolute differences can't all be the same. And so as a result, A cannot contain 3 different elements, so it can contain at most 2 elements. And clearly any set of 2 elements is fine because if we have, or because there's only one absolute difference between a pair of those elements, so that's going to be all right. Okay, so let me show you my code real quick. So the first thing I do is I initialize the answer to the minimum of n and 2, and that's to handle this case. If we have at least 2 elements and we can take them, this min thing is meant to handle the case where n is equal to 1, in which case we can only take the 1 element. Then I create this map that's going to store the count of the number of times each element appears in the array, and I increment the count for each element that appears. And then I iterate over each of the members of the count map, so each of the elements that appears at least once. And I set the answer to the maximum of the answer and the number of times this value appears. So that gives us the number of values that we can keep. So then the value that we have to remove is n minus the number that we've kept. Okay. Yeah, so that's the problem. I'm going a little quickly because there are a lot of problems to get through. There are, I think, 9 that I'm planning to discuss. But if anyone has any questions, please feel free to put them in the chat, and I will get to them when I can. All right. So the next problem is, someone asked what's the template for traversing. So this thing trav just traverses over every element of a data structure, whether that's a map or a vector or a set or anything like that. And the code that defines it is here. Define trav of ax just to be for auto reference a in x. All right, so team formation. Essentially, we're given a bunch of individuals where every person might know about programming and they might know about English, and ultimately we're going to need to form teams of 2 such that within each team, at least one person is going to know programming and at least one person is going to know English. And we need to find the maximum number of teams that we can form. And for the person asking if you can get my template, if you look at my CodeForces profile, you can find my template on any of my submissions there. I'll put a link to my CodeForces profile in the chat. Okay. So here we can essentially do a greedy strategy. The idea here is, so first of all, let's think about the participants who know neither programming nor English. They're going to have to be partnered with somebody who knows both. So let's do those matches first. So let's match up the people who know neither with the people who know both until we're out of either one of those 2 groups. The next, and then let's think about, for example, the participants who know programming but not English. So they have to be partnered with participants who know who know English. And for this, the greedy observation is that we should prioritize the participants, or prioritize the potential teammates who only know English and don't know programming. Because at that point, when their team, or because at that point, the people who know both, there are more options for who we can partner them with, and so we're sort of minimizing the amount of knowledge that we waste. And similarly, so then we made a bunch of matches with the people who know programming, or who know programming, to the people who know English. And now what we're left with is we've got maybe some people who know both, and then we've got these 2 groups. So with all the leftover individuals who know one of programming and English, but not the other. We're going to match these with people who know both skills. And the idea there is that these people we can't, or the only way we can match them up is to match them with people who know both skills. And finally, we're just going to match people who know both skills with each other, because at that point they're sort of all we have left. So the general idea here is we're trying to essentially go start with the lowest, or the people with the fewest skills, because it's going to be the hardest to make use of them, to put them on a team. And then once we're out of those people, then we look at the people with more skills. So I'll show you my code. Essentially, I read in the choose strings, and then I number the four types, 0 through 4. The idea here is that if someone knows neither skill, then they're gonna be in category 0. If they know programming, or if they know English but not programming, that's category 1. Programming but not English, that's category 2. And then both is category 3. And the reason that this works well is that this makes the categories very easy to compute. If for an individual their character in S is 1, then we add 2, and if their character in T is 1, then we add 1, and then we just increment that count. And now count stores the number of people in each category. Okay, so first thing I do is I try and form teams of people who know both skills with people who know neither. So I take the minimum of those two values and add it to our answer, and then I remove it from the number of people who know both skills. Next, I try and make teams out of the people who know, out of like the 2 people who know different skills. And so again, I find the minimum value, and then I add it to the answer, and then I subtract it from the from each of those sets. Then we might have either some leftover people in category 1 or some leftover people in category 2. So I try and match up those leftovers, which are in this max expression, with the people who know both. And so I add that count to our answer and subtract it from the number of people who know both. And finally, I try and match the number of people who know both with each other, and the number of ways we can form is just half of the number of people left. Okay, this is kind of a difficult one to explain, but I think overall it just sort of comes down to thinking through all the cases and making sure you're not missing everything. So in essence, I give you my code to review. Unfortunately, I don't have time to review every program that people submit to me. So I'd recommend maybe posting it on the CodeChef forum and seeing if you can get some help there. Someone asked why is this last part half? Because we're going to need 2 of these people for each team, and so if each team takes 2 people, then the number of teams we can make is half the number of people. All right. Let's look at so we're going to do chef enclosure next, and then we'll move on to the problems from div 1. We're given an array A of n integers, and we have to determine whether this array is closed under multiplication. Okay. So the key observation here is that there has to be at most one element of A with absolute value greater than 1. And the reason that this is true is that when we multiply 2 numbers with absolute values greater than 1, we get a third number with an even greater absolute value. So like for example, if we multiply 2 by -2, those both have absolute value 2, we get -4, which is absolute value 4. And so for example, if we have 2 and -2 on our set, then that means -4 has to be in our set. But then that means 2 times -4 or -8 has to be in the set. So 2 times -8 or -16 has to be in the set, and so on. And so in general, by repeatedly multiplying I guess actually the easiest way to explain this is to say, consider the two numbers with greatest absolute values, and say they have absolute values x and y. Then their product has absolute value xy. But if x and y are both greater than 1, xy is going to be greater than x and y. But x and y are the largest absolute values in our array. So this is a contradiction. Okay. So what that implies is that the answer is no if A contains multiple values with absolute value greater than 1. So we can now assume that we might have a bunch of, or so we're going to have a bunch of 1s, maybe some 0s, maybe some -1s, and then one larger value, or at most one larger value. I guess not necessarily larger, but at most one other value. And from here, we can essentially brute force the idea, or because because even though there could be a lot of different, you could have an array of, let's say, 10,000 1s and 10,000 0s and 10,000 -1s, the number of distinct multiplications you can perform is actually pretty small. And so a properly implemented brute force can work from here. But alternatively, you can an observation you can make is that if the set we only need to check multiplications containing at least one -1. So we need to check -1 multiplied by each value in the set. And the idea here is that if we multiply something by 1, it's not going to change. If we multiply it by 0, we know we're going to get 0, and that's going to be in the set. And so that means that any multiplication that could possibly mess us up is going to have to include -1. So I'll show you my code. I actually need to edit something real quick. I realized I didn't have the chance to submit my code for the div2 problem, and I realized I made a slight error. So let me edit this real quick. Okay. So again, here I store the count of numbers with absolute value greater than 1, and then I store the number of times each value appears. If there's at least more than one of these, then I return 0. Otherwise, if -1 is in the set, then I iterate over each element, and if -1 times this element is not in the set, then I print 0, and otherwise I print 1. The special case I just added is we have to make sure that if -1 is only included once, then we aren't testing the case where we multiply it by itself. So if the first value is, we make sure that either the first value is not -1, or if it is -1, then it appears multiple times. Okay, yeah, I'm not 100% certain I haven't missed an edge case. I haven't had the chance to submit this, but I think this is definitely the general idea, and the key observation is definitely this idea. All right. Okay, so now I'm going to move on to the problems that are in Division 1, and we're going to start with different string. Oh, whoops. Okay. So we're given n strings, and we have to find a binary string of length n that's different from all of the given strings. Someone asks, what is, I'll talk about my code in a moment. All right, so this one is pretty, so this one, the idea here is that n is small. There aren't really that many strings, So if we can generate m plus 1 binary strings of length n, then we're done, because one of them has to be distinct from the input set. Now there are a few ways you can so one way you can do this is you can construct the strings 1 0 0, or so let's say the n is 4, for example. You can construct the strings 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1, and then in order to get a fifth string, you can get 0 0 0 0, and you can just check which one of these works. So that's one way to do it. Another way, which is mentioned in the chat, is you can use something similar to the Cantor diagonalization argument, where essentially you can generate a string directly by iterating over the input set and essentially construct a string that is distinct from string I in position I. And so, for example, we want to avoid matching the first string in position 0, so we're going to put a 0. If we want to avoid matching the second string in the second position, we need to have a different character from this one, so we put a 0. And to avoid matching the third string in the third position, we put a 1. So that's another way. The way I did, which I will admit is less nice than either of these approaches, is to just generate strings in lexicographical order until 1 works. Or lexicographic order. So I read in the input strings, and then I initially build a string t, and I initialize it to just be all zeros. And then I just repeatedly check if the current string is valid, and if it is, then I output it. And otherwise, I find the last 0 in t, I replace it with a 1, and then I turn everything else into zeros, and that computes the next string in lexicographic order. I'm being told that this same problem has also appeared in LeetCode. Yeah, I know there's been a similar problem on CodeForces, I think. I can't remember. Yeah, actually, no, I remember which problem this is. I'll pull it up. It's called a bit similar, I think. Yeah. So this the inspiration for my solution is this problem from a recent CodeForces educational round called a bit similar, where essentially you're trying to construct a string or find the lexicographically smallest string that matches an input string and all substrings of length k. And the idea there is that there aren't that many strings you need to check, so you can just repeatedly generate the lexicographically minimal string and you'll be fine. So that's sort of why I implemented it like this, but I do think the other ways are probably nicer. Okay, so the next problem is clear the array. We're given an array A of n elements, and we can either remove the leftmost or rightmost element of the array with cost equal to the value of that element, or we can remove both the leftmost and the rightmost element for a cost x, and we can only do that k times. All right. So the key observation here is that the positioning actually doesn't really matter, and what that means is let's just pick the elements we want to remove using operations of the third type. Then, as long as we've chosen a valid number of elements to remove, i.e. it has to be even because each of these operations remove 2 elements, and it has to be at most 2k because we can only remove 2k elements in this manner. Then we can remove these elements using the third type of operation, and the remaining elements using the first 2 types. So for example, in the second sample input, let's say that we decide we want to, well actually no, this is a bad example. I guess unfortunately there aren't really any great examples here from the sample input. But let's say that we have an array of 6 elements, and we decide we want to remove the third or the second. Actually, let's say we have 8 elements, and let's say we want to remove the second, 4th, 6th, and 7th using operations of the third type. Well, then what we can do is we can remove the first element, then the last element, and then we can perform a type 3 operation, then remove the first element, type 3 operation, then remove the last element. And in general, we can just proceed in this manner, working our way inwards in order to remove whichever elements we want using the third type of operations. So we've made this into a much simpler problem, because what we need to figure out is which operation, or is which elements, or sorry, on which elements should we perform the third type of operation. And the idea is this. Suppose we're performing the third operation n times. Then we should perform it, then our answer is equal to x times m for the cost of those operations, plus the sum of the n minus 2m elements we didn't pick. So we should pick the largest 2m elements for these operations and remove the remaining, or the smaller n minus 2m elements manually. And so that means that we can do a greedy approach. Essentially, we can repeatedly try and remove the first two elements, as long as doing so will actually decrease our answer. So as long as their sum is at most x. I'll show you my code. I read in the array, and then I sort it in decreasing order. And initially, I say we're performing no operations. So I set the answer to the sum of all the values. And then for the up to k element, for each of the up to k operations, first, I just make sure that I'm not going out of bounds in the array, which actually isn't necessary because we're given this constraint. But then if x is less than the sum of the next pair of elements, then I add then I remove this sum and add x to our answer, signifying that we're performing this third type of operation, and then I print the answer. Someone's asking how to optimize a DP solution. The answer is that you shouldn't. You should just do this greedy. There's really not much of a reason to do DP here. At least like once you make the greedy observation. I can definitely see how it would be tempting initially. I should also note here, well actually no, I mean I think it's mildly silly that they have 200 tests with n up to 5,000. Like there's really no reason they couldn't have done it like the other problems where the bound on n is relatively large, and then there's just a bound on the sum of n over all test cases, but it doesn't really matter anyway. Okay. So next problem is odd array. We have to construct an array of length n containing only positive integers in the range 1 to 1000, such that there doesn't exist a subarray in which every element occurs an even number of times. And we can output any solution if multiple solutions exist. Okay. So let's think about the problem like this. So let's say that the maximum element we are using is m. What's the largest possible n we can achieve? So in other words, given a certain maximum element, what's the best we can do with that element? I played around with this for a little bit, and the construction I came up with is is as follows. So what I do is I go 1 2 1 3 1 2 1 4 1 2 1 3 1 2 1, for example, if the maximum element is 4. And in other words, if I index the numbers from 1 to n, so like 1, 2, 3, 4, 5, 6, 7, and so on, then I'm saying a of I is the maximum power of 2 by which I can be divided. So for example, the maximum power of 2, actually sorry, no, this is an incorrect way to define it, is 1 plus this thing. And so, for example, for 1, the maximum power of 2 it can be divided by is 2 to the 0, so we put a 1 here. With 2, the maximum power is 2 to the 1, So we put 1 plus 1, which is 2 here, and so on. I don't have a proof that this is optimal. I sort of just, it felt really clean, so I decided to implement it and go for proof by AC. I'm guessing that there's a pretty easy proof that this is optimal that I just came up with. Okay, so then the idea here is that we can achieve at most 2 to the m minus 1 elements. And the reason this is optimal is, let's think about the, I'm trying to think about the cleanest way to define this. So essentially, consider the set of elements appearing an odd number of times in each prefix. So for example, for the prefix 121 here, this set is going to contain only 2. If there are 2 prefixes where these sets are equal, then the array is bad. And the reason is that, let's say that the set from 1 through L equals the set from 1 through R, where L is less than R. Then we can show that the array L plus 1 through R contains every element an even number of times. And that's because if this array contained an integer an odd number of times, then these 2 sets would not match, because that integer would sort of be in one set but not the other. So what that means is that all these prefixes have to correspond to distinct sets. Now, given an integer m, there are 2 to the m distinct sets containing, or 2 to the m distinct sets of the first m numbers. So there must be at most 2 to the m prefixes. And in fact, for a given n, there's going to be n plus 1 prefixes. The empty prefix, the prefix of the first element, the first 2 elements, and so on, all the way up to the first n elements. And so m plus 1 is less than or equal to 2 to the m. So n has to be less than or equal to 2 to the m minus 1. And that tells us that you can't do any better than this. Now, it remains to show why this actually works. And the idea is this. Clearly, our answer cannot contain the largest element, because this largest element appears only once. Like here, for example, there's only this 1 4. So what that means is that our subarray cannot contain this 4. So we have to look either within this left array or within this right array. But then within either of these arrays, it can't contain the maximum element of 3 because there's only one of those. So we have to look within this array or within this array. And in general, we can sort of proceed inductively. We can never contain, we can't use the largest element, so must go to the left or the right. But within either of those arrays, the largest element appears once, so we can't use the largest element there either, and so on. And so this ends up being valid. As far as my code, it's very short. I just print 1 plus built-in CTZ, which is the number of trailing zeros, which is equivalent to the way I've defined this maximum power of 2 here. Yeah, so that's, I guess, all there is to say about this one. Someone asked, what's my WPM? Depends on the day, but anywhere from 100 to 150 most of the time. Okay. Let's talk about interactive equivalency. I think this is my favorite problem on the contest. So we're saying that 2 arrays are equivalent if for every, if 2 elements of the second array are equal to each other if and only if the corresponding elements in the first array are equal to each other. We're given an array of, or there's a hidden array of n integers, and we have to construct an equivalent array to the hidden one. And so if And we're allowed to perform up to 6n queries, where in each query, we're going to print out a subset of the indices, and we're going to be given the frequency of the most frequent element among these values. And we have to, and then so we can just print out any answer if multiple exist. Okay. Now, it seems like it's going to be hard to say something particularly general about the whole array. Like, for example, if we queried the whole thing, we could get the number of the times the most common element occurs, but it's hard to say like how that's going to help us. So instead, let's build the answer inductively. So for n equals 1, the answer is just a single element. That can be whatever we want. The answer is just 1. And so now, we need to figure out how to find element, let's say I, if we already know elements 0 through I minus 1. All right. So the idea here is this. So let's create a set that I think in my code I call it cur. And that's going to be a set containing all the positions with distinct values. And so, for example, in this array here, these first 3 positions would be in cur, but this last one would not. So it's going to store like 1 position with each value present in the array. And so the first question I'm going to ask is does element I appear in A of 0 through I minus 1? And what we're going to do is we're going to query cur and then also the element of I. If the answer is 1, then I does not appear. So I represents a new element of the array that we haven't seen before, and we can append it to cur. Otherwise, I must be equal to some element of cur. And so then the question is, how do we figure out which one? And the answer is we binary search. And so what we're going to do is we're going to query half the elements of cur with I. If the answer is 1, then if the answer is 2, then I must match some element in this set. If it's 1, then I must match one of the other elements of cur. And so by repeatedly querying in this manner, we can reduce the set of elements we're considering until it only has size 1, and that's going to give us our answer, or the element that's going to be equal to I. Someone says, do you have to binary search, or could linear search also work? You have to binary search, because if you did a linear search, then you would need O of n squared queries, which is much too slow. Thanks to binary search, we use O of n log n queries. There's some constant factor issues involved in that, like, we either are going to just append an element to cur after one element, or we're going to take log n operations. But you can quickly verify that this is going to be fine because log n is about 6 and q is up to 6n. So I'll show you my code. I just have this boilerplate function to actually perform the queries. So then I set the first element to be 1, and then I create this array integer next that's going to store the value of the next element that we haven't seen yet. So first, I actually call this array vals, not cur, sorry. And so then for each element, I add that element to values, and query it, and if it gives us a 1, then we have a new element. And otherwise, this matches an element that's already in vals, so I pop from the back of vals. And then I binary search for the position in vals that's going to match up. So essentially, if we're looking at the interval low through high, then I pick a mid in the intersection, and then for all the elements low through mid, I push them to this array cur. And if it matches something in cur, then I set high to mid because it has to appear within the interval low through mid, and otherwise it has to appear within the interval mid plus 1 through high. Someone says no Kickstart round screencast. Take a look at my channel. I posted my screencast for that round earlier today. So then I set the answer for this value to be the same as the answer for the matching position. And then I print out the answer. All right, last problem. Chef to chef. So we're given an array of length A, and we have to choose an array with at least 2 elements. Then the chef is going to pick out 2 elements of this array, and our score is going to be the sum of the remaining elements of the array. Oh, before you get to this, by the way, Alfred asks, can you give some tips on how to test interactive problems locally? Normally, I would just like read through the queries and type them out by hand, and just type them out by hand, just sort of just testing them by hand. And so I can show you what it looks like when I run my problem D on the sample input. Let me just see what the sample input was. So 1 and then 3, 18, and then I know the hidden array is 10, 20, 10. So the most frequent answer the most frequent value among values 1 and 2 appears once. Most frequent value among values 1, 2, and 3 appears twice. Most frequent value among 1 and 3 appears twice. And then I get the answer, so I say okay. So just like that, just sort of manually testing it. My video, My Competitive Programming Setup, has some details on how you can automatically test interactive problems, but I wouldn't recommend that unless you're submitting and you get WA and you have no idea how to what test is breaking your solution, because that forces you to actually write an interactor, and that can be a huge pain. So I would just say manual testing is going to be your friend here. All right, so chef to chef. Now, an obvious observation here, or I shouldn't say obvious, but this one really is pretty intuitive, is that chef will remove the largest 2 elements of your array. And so we have to pick some subarray that maximizes the sum of this subarray minus the greatest 2 elements. Now, in general, an issue here is that we could have n squared subarrays, and it could be hard to figure out what the greatest 2 elements are, and so on. And so for problems like this, usually what we're going to do is we're going to like fix. We're going to hold something fixed, and then we're going to use a data structure. And what I figured out here is that we should fix the second largest element, or rather iterate over all possible second largest elements. Then let's say that we're picking this element in position P as our second largest element. And let's say that on the right, the nearest large elements larger than P are like X and Y. And then on the left, let's say we've got B and A. And so B, A, X, and Y are all larger than position P, and all of these elements in between are smaller. Then our subarray has to contain at either position A or X, but not both, and neither position B nor Y. So the idea here is that P has to contain exactly 1 larger element, so we can take this array P through A and then maybe some of these elements on the ends, or we can take P through X and maybe some of these elements on the ends, but not both. So this characterizes the subarrays we can take whose largest values are P, and it even tells us whose second largest values are P, and it even tells us what the largest values are going to be, because in this case the largest value is going to be A, and in this case the largest value is going to be X. And so now we need to figure out how to find the greatest possible sum of the subarray. And here we're going to use the key algorithm to use is going to be prefix sums. What we're going to do is we can essentially represent a given subarray as the difference of 2 prefixes. So for example, this subarray here is equal to the difference, this prefix minus this prefix. So we want to maximize the sum of the right prefix and minimize the sum of the left prefix. And so, for example, if our value is going to contain p through x, then we want to find the largest prefix ending somewhere in this range and the smallest prefix that ends before p, and we're going to subtract, or sorry, the smallest prefix that ends somewhere in this range, where we're going to make sure we're subtracting out a, and but overall we're subtracting out as little of the sum as possible. And that's going to be the best array whose where the largest two elements are p and x. And so then, how do we find the minimum and the maximum prefix sums within a given range? These are just range maximum and range minimum queries, which we can answer using a segment tree. So let's talk about my code. So first of all, I just defined the segment tree seg1, and that's going to store the maximums, and seg2, that's going to store the minimums. And then I read in the prefix sums and update the segment trees accordingly. So then I'm going to store this array vals, and vals is going to store each value and combined with the corresponding position. And I'm going to sort it in descending order, so we're going to get iterate over the second largest position in decreasing order. Then I'm going to maintain this set of values that we've used already, and I add the two ends of the arrays, this -1 element that comes before the first value and n that comes after the last. Okay, so then I find the position p, and I use the set to find this value x1, which matches x in my explanation here, and this value y1 that's here. And if x1 is not like all the way to the right of the array, that is, if there actually is some larger element than p to the right of p, then I find x2, which is this value y, and then I set the answer. And the answer is going to be the largest prefix on this interval that's going to include x but not include y, minus the smallest interval minus the smallest prefix that needs to include a because we want to delete a but not p. And then I subtract out the two large elements. And the other case is similar. I use my set to find the value y2, which matches b in here. And I find the largest prefix that contains p but not x, and subtract out the smallest prefix that contains b but not a. And that gets us the answer. So then I insert p into our set, and I print out our answer. So yeah, that's the contest. If there are any questions in the chat, I'll be happy to answer them. But otherwise, I think that is all I have today. Thanks to all of you for sticking around. I'm curious, I wonder if they posted editorials yet. I think I had the right general idea for this 6th problem in Div 1, but the implementation was really annoying. What about the last problem? Okay. All right, well, I'm going to go ahead and shut off the stream. So thanks to all of you for watching, and I will see you